Hi everyone, this is your struggling CS student, and today I'll be solving the LeetCode daily problem. So let's take a look at today's problem. I've not solved this problem before. It's a almost 2000 rated question. So the question is 1625 lexicographically smaller string after applying operations. You are given a string S of even length, okay, consisting of digits from 0 to 9 and two integers a and b. You can apply either of the following two operations on you can apply either of the following two operations any number of times in any order on S. Okay, even length of only digits and two integers a and b. Okay, so you can add a to all the odd indices, zero indexed. Okay, digits post 9 are cycled back to 0. Okay, so if it's S is 3, 4, 5, 6, you can add A, and A is equals to 5. S becomes because okay. So this is the odd indices, and this is another odd one. So 4 plus 5 is equals to 9. 6 plus 5, then you round it back. I think you can just mod it by 9. You get 1 back. Or is it mod by 10? I'm not sure. Let's see, 6 plus 5, you want to get 1 back. I think you need to mod 10 instead. Yep. So, so you can either add A or you can rotate S to the right by B positions. So if this is the string and B is equals to 1, you can rotate right, so 6 goes to the front. You want to return the lexicographically smaller string that you can obtain by applying the above operations any number of times. Okay, so a string is lexicographically smaller than another string, the same length within the first position where they differ. A has a letter that appears earlier in the alphabet, blah blah blah. Okay, okay. Yep, yep. Hmm. Okay, I mean, my first thoughts are immediately either, okay, let's check the constraints first. Oh, the constraints is only 100. Okay, that means something around n cubed will actually work. It's even, A is only up to 9, okay, makes sense. B can rotate up to, well, I can basically rotate almost everything. So, okay, acceptance is 73%. Damn, okay, shit. Why is a 2000 rated question though? So my thoughts are immediately either dynamic programming, where we apply the operation and we, just say, we might revisit states. I'm not exactly sure if dynamic programming is the way, so we just kind of like brute force our way to the answer. Another approach that I'm taking off is maybe we can identify some sort of greedy principle that we can abuse in order to get a direct answer. So at every step of the way, there must be an optimal there must be an optimal move locally that when applied at every single position that we can apply it, it leads to a globally optimal answer, right? But it's not immediately obvious to me how that can be done. So let's take a look at example 1. So S equals to 5525, A is equals to 9, and B is equals to 2. Because we want the lexicographically smallest number, we always want to try to minimize the first character to be the minimum as much as we can, right? So in that case, let's see what they do. They actually rotate it twice, so you get this. Then you add it to the even position, the odd positions. Yeah, you add it to the odd positions. So this is so it's 4 plus 9 mod 10. Yep, we get 13. So okay, afterwards what did they do? They rotate it again, and then they add it again to the odd positions. Wait, how did they get? Because they rotate, they get this, then they add again. Wait, hold on a second. Rotate it by two positions, they add it. So after adding, you get this, right? Because 9 plus 5, it's 14 mod 10. Okay, then you add again, you get this. Then rotate it by two positions. So you have 5, 3, 2, 3. Okay. Then you add 9 again. 9 plus 3, that is 12 mod 10. You get 5, 2, 2. 5, 2, 2, 2. Okay. You add it again. So it's okay. Then you rotate it by two positions. Then you add it again. And then there's no other way to obtain a string that's lexicographically smaller than this. But when do we stop? I'm thinking like if we go with the DP approach, when do we stop? Because there doesn't seem to be any principle, any sort of like greedy move that we can make locally. Like for example, at this string, right? Right, 5525. Like we can either move it by two positions to the right, or we can add it at this. But when do we choose one over the other? If one can give us a better answer, I'm not sure. But it does seem like, at least from this position, right, from the starting state, you would want to rotate it twice, right? Want to rotate it twice because then you can put two at the front. But I'm not sure if like locally selecting the best possible move will actually result in a globally optimal answer. For example, right, you see in this case, I don't think radio would actually work. You actually need to make the optimal move at each step of the way, even if it means taking one step back and moving two steps forward. So what do I mean by that? So actually, if you look at from starting state, yes, we rotate two, we get into a better position because we want a lexicographically smaller string. And then we add again, and this gives us an even better position. We add again, gives us an even smaller string. But look at this. We actually rotate it for reasons we can't know at this stage, right? Because we can get a better answer by reaching a state where uh, it's not strict. It's not like a strict improvement because you can see like from this string, we actually after rotation we get to a lexicographically larger string, right? So in this case, I'm leaning towards dynamic programming. However, this could still be tricky, right? Because like when is the base case? When do we stop? Maybe. So let's see in this case, this is the answer state, right? If we move it by two positions, we get 5020, right? But that's not better than this current state. How about we add 9, right? If we add 9, right, 2959, it's also not a better state, but that's not good enough. Hold on. That's not good enough because even though adding or rotating gives us like a strictly worse answer, and you might think like, oh, maybe that's the end state. But here, we already seen that from this state, you can actually do a rotation and bring yourself to like a worse state, but somehow reach a better state in the future, right? So maybe dynamic programming, but we don't know when to stop. We don't know when to stop. Or maybe it's backtracking. Maybe it's backtracking. No, s dot length is 100. There's no way it's backtracking. Yeah, there's no way. Because then like at every step of the way you have two operations, right? So in terms of the tree, I can just draw it out. In terms of the tree, what you will get is you have your starting state. You can either do an addition or you can do like or rotation, right? But this is at the, wait, let me see. Maybe, yeah, actually, maybe backtracking is just straight up wrong. Yeah, I think backtracking is just straight up wrong. Never mind. Okay, in that case, that would definitely be just dp then. Okay, if it's dp, what is the base case? What is the base case? Or maybe it's something else altogether, I'm not entirely sure. Even length. I'm trying to think if like there's a cycle kind of thing, then you would like somehow stop. Let's see, from 2050, 2050, you can add 9, right? We can either add, right, it'll be 2, 9, 5, 9, or we can rotate it by 2. That'll be 5020. 5020. Have you seen 5020? Nope. How about 2959? No. Now where do we go from here? Suppose we add, let's see, get apply either of the following two operations on any number of times and in any order. So what if we do a rotation here? If we rotate here, it'll be 5, 9, 2, 9. If we add, that'll be 9 plus 9, right? 9 plus 9 mod 10, that'll be 2, 8. 5, 8. Can we add again? That's 8 by the way. If we add again, that would be 2, 1, 5, 1, right? So 9 plus 8, wait, that's 17. 17, 17, there's 2, 7, 2, 7. Well, we add again, that would be 2, 6, 5, 6. Then we add again, and it just turtles all the way down. I mean, we'll eventually reach 2050 actually. Yeah, we actually just eventually just reach 2050. 2050. Okay. Right, because 6. So from here, you add 9. Right. Afterwards, you add 9, you add 9 again, you add 9. So 9 plus 6, that's 15 mod 10, 5. Then just all the way to 0 again, then you actually reach back to the same state, right? So what does this tell me? Actually reach back here. And this is the best that you have seen. So I guess if you revisit states, that's when you're done. Okay, let's take a look at the rotation one, right? In this case, if you rotate it by 2 times, right? Let's say you do the rotation again. Let me see. Let's say you do the rotation, you get 2959. You actually just get back the same string. Right, after a certain number of rotations, you just get back the same string. Is that always true? Is that always true? Let's see. So suppose 2959. Suppose your rotation is 3 instead. Right, let me see the rotation constraints. It's interesting that you always go to s.length minus 1. Right, it kind of makes sense. If it's s dot length and you rotate it s dot length number of times, then you just get back the same string. So if you rotate it twice, right? Because like obviously if you rotate it once, if r is equals to 1, you can just rotate it 4 times, you get back the same string, right? But if suppose the rotation is 3 instead, so you rotate it twice, so I put 9, 5, 9, 2. You rotate it twice again, you get 2, 9. So this goes in front, this goes in front. Okay, 2, 9, 5, 9. Okay, you actually get back the same one. So there is some sort of like cycling that's going on, I think. So in this case, let's so if you rotate it twice again, you get back the same one. You rotate it twice again, you get back the same one, right? This is the rotation operation. So you can only really make a move, right? As in you can only affect the state by adding, from this example at least, by adding, by doing the addition operation. So let's say if we do the addition operation here, right? We do the addition operation. What do you get? Let me just make this a little bit nicer. Do the addition operation on the odd indices, right? On the odd indices, you actually get 5, 8, 2, 8, 5, 8, 2, 8, 5, 8, 2, 8. No, I mean this is 5, 7. Oh, okay. So you eventually you might get to like actually 5, 0, 2, 0. Is that the starting string? 5020 is not the starting string. It's not the starting string. But what I'm noticing is actually you can change the positions, or at least for this particular example, you can change the the character at the odd position, right? 5020, and if you add 9 again, you come back here. Okay. Interesting. Interesting. So it starts like this. We rotate it. So we add. At this position, at this time, when we rotate it twice, the 2, let's see the example. 2, 3, 5, 3, and we do a rotation. 2, 3, 5, 3, do a rotation, becomes 5, 3, 2, 3. And then we can modify the odd positions. Here and here. We reduce it to 2, right? Yeah, we did. We reduce it to 2, reduce it to 1, then we do the rotation and then reduce it to 0. So what doesn't change? It seems like the odd position, the 0, 1, 2, the even position numbers can never change. Right? That's like one of, maybe like I can add that even positions doesn't seem like it can change. That's not like a very good description, but yeah, even position characters, I guess, doesn't seem like it can be changed by the operations, right? This is observations. Maybe I can say 1 dot. All right. What's the second observation? There seems to be some sort of cycles cycle where it where if you add where if you perform the add operation enough times, you actually go back to the original string. Yeah, I would say these are weak observations, right? Basically, I'm not sure if they always hold. So what about number 3? If that is the case, I mean, if all these observations hold, then what we can do is we'll try to move the, like in the odd positions, sorry, in the even positions, we move the smallest character in the even positions to the start if we can. Okay, then we try to minimize the odd number um, characters by performing the add operation, right? I think the example might be trying to troll us. Let's see if the example is trying to like confuse us, right? Because after you do this, right, you can just add 9 again here. Why do we do the rotation here? I have no clue. Let's see, 2, 3, 5, 3. So maybe there is some sort of greedy principle, after walking through the examples. So 2, 3, 5, 3. We do an add operation. We add 9 here. We add 9 here. 9 plus 3, that's 12. Mod 10. You get 2, 2, 5, 2. You just add 9 again. 9 plus 2, 11. Mod 10, 2, 1, 5, 1. You add 9 again, and mod 10, you get 2, 0, 5, 0. Right? So why is there these operations? I have no clue. I don't know why LeetCode is doing its own thing. Okay, let's take a look at this, right? Even positions doesn't seem like it can change. There seems to be some sort of cycle where you perform the add operation sometimes. You go back to the original string. Even positions, you can't change this, but you can change this. In this case, the rotation is 1. So you can't change this. So you do the swap, and then you can change this. So 7 plus 5, 7 plus 5, that is 12. 12 mod 10, get 2. 2 plus 5 again, 7, so they don't want to do that. Then you get 42, and then you can rotate it. Okay, so sometimes, if you can rotate the even positions to odd positions, then you can minimize it. As if you can move the even positions to the odd positions, then you can minimize it, yes. Oh, I accidentally clicked the back button. But you see here, right? We rotate it back. We get 2, 4. We add 9, get 29. But from 29, we add 5 again. We actually get back to 24. And maybe that's the best that we can do. Some sort of cycle detection. I'm not sure. Let's see. I think that actually, right, the fact that the string s is always of even length, that means b. I'm not sure if b being odd or b being even actually affects anything. I actually wager it probably does. Okay, so let's see. Here, in this case, b is actually even. There are no sequence of operations that give us a lexical smarter string than this. Okay, so let's try it out. Right. So 0, 0, 1, 1. So in this case, I'm actually leaning more towards making some sort of like greedy observation, because DP seems to be hard. You do not know what is the base case, and even if you track like what you have already seen, it can be quite tricky. Yeah, at least that's what I think. So Okay. Okay, let's say 0011, right? In this case, your rotation is even. That means you can do 1100 and you can affect this, right? Let's make it nicer. You can change, oh, you can change this, but you might as well just change this, right? Right, by performing the add operation. You know, instead of affecting this, you might just change the ones here. So let's see. In this case, you can add 4, 0, 4, 1, 5. Add 4 again, 0, 8, 1, 9. You add 4 again, 0, 2, 1, 3. Right? Add 4, right? Yep. We add 4 again, 0, 6, 1, 7. And 0, 0, 1, 7 plus 4. 7 plus 4. Yep. So you actually just go back. You just go back, right? Yeah. Okay, okay. Maybe we're getting somewhere. Okay, what if, let's take a look at this example. What if rotation is actually equals to 1, right, in this case? And actually, I'm using 2. Yeah, okay. Reset the zoom. Okay, 0. Oh, holy shit, that's huge. 0, 0, 0, 1, 1. And let's say rotation, right? The rotation is equals to 1. Let's keep A the same. So now we can definitely move the odd positions, I mean the even positions into the odd position, and then we can try to minimize it, right? That's the key. That's the key. So here's this. Let's do one rotation. We get 1, 0, 0, 1. We can minimize this. We can minimize this. Actually, in this case, kind of doesn't really matter. 1, and we do one more rotation. That bring us back to the same position. We can try to minimize this or minimize this. Okay. Okay, let's see this one. Minimize this. Hey. Well, this is already minimized. So can we minimize this? I don't think we can. I don't think we can. This is like already the best answer. How about this one? 5525 with v is equals to 1. So that's 5, 5, 5, 5, 2, 5. You know, a is equals to 9 and b is equals to 1. Right. So in this case, we can only minimize this, right? So we can do a rotation. So we want to put the largest numbers here, and then we shrink it down with the largest numbers and in the odd positions, and we'll try to shrink it down. In this case, it actually, the largest numbers are kind of already here. Then in that case, we also want to move the smallest number, smallest index to the front. Actually, no. So we know that in this case, we actually can shrink it down all the way to 5, 0, 2, 0. But because b is equal to 1, we can perform a rotation. So we do the add operations here, right? Dot, 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 we get 5, 0, 2, 0. We do the rotation operation once. We actually get 0, 5, 0, 2, right? We do rotation. Then we can actually shrink this down all the way to 0, 0, 0, 0. And this will actually be the best answer. So let's try that. So just do this. Just as an experiment. I actually think that would be 0, 0, 0, 0. 0, 0, 0, 3. Wait, why is that? Oh, must be because of the relations. Let's simulate it, right? We do the add operations. So 5 plus 9, that's 14. Okay, we can shrink it down to 0 because they are the same number. 0, 4, 0, 1. We can shrink it down again, right? 0, 3. Actually, we can just do the rotation in this case. Actually, can we? Yeah, we can. Okay, let me just erase this first. We can actually rotate it such that it's 2, 0, 5, 0, and then it's 0, 2, 0, 5. We add 9 in this case. We get 0, 1, 0, 4. We add 9 again, 0, 0, 0, 3. Okay, so this is the best answer. So what does this tell me? This tells me that it's not that the even position characters can't be changed by the operations, but if you can move them into an odd index, you can actually change that. Okay, this is when b is equals to 1. What if b is equals to 3? Because if this is even, right? If b is equals to 2, we can never move like this bit. The even positions actually become fixed, right? So when b is even, you can't actually change the even position characters. So it's not that this is, oh well, that's wrong, but it's more like this is more correct. Yep. But let's confirm that, right? So suppose a is equals to 9 and b is equals to 3. We get an even length character always, right? So if it's 5, 5, 2, 5. So when b is even, you can actually change the even position characters. When b is odd, you can you? So we can move this 3 times, right? If we move this 3 times, so they're 1, 2, 3, right? Get 5, 2, 5, 5. Oh, I have to 5, 5. So this was 0, 1, 2, 3. We move it 3 times, so this is 3, 2, 3, 2, 1, 0. This was its old indices. The new indices would be 0, 1, 2, 3. So you can actually see that the odd position went into the even position, right? 3 to 0. And the previous even position actually went to odd position. So I venture to say that when b is odd, when b is odd, you can actually change the even position characters. Well, if you swap it back, get 5, 5, 2, 5, for which is the original string, right? If we do another rotation, so in this case, what would the answer actually be? What's b? What's b? We do an NQ operation. B is only up to s dot length. Okay. You know what I'm thinking? I'm thinking maybe we can do a rotation. We do all the rotations until we reach back the original string. But we always try to do the add operation until we reach a cycle, and then we just keep, in essence, kind of brute forcing the answer, if that makes sense. Yeah, I think maybe we can give that a try. I'm not sure if it will work, but the algorithm would essentially be, so it doesn't really matter whether it's even or whether it's odd. We just do the rotation, we minimize, we do the rotation, we minimize, we do the rotation, we minimize. Right. If we have not seen, we can keep doing the operation. I think we could give that a try. Not entirely sure. Scene is equals to set. So we say while s not in scene, say scene dot s, we would do the rotation and we return main of scene, something like that. So we do the rotate, we rotate s. We do the add operation, add s, add s. For s not in scene, dot add s, then we do the add operation on s. Maybe I should call this add operation, make it more clear. Add operation. S not in scene, add operation. Then we do a rotation. It's a bit tricky. It's a bit tricky. It's a bit tricky. Let's see here. 5525. Let's do a walkthrough instead. 5525. We do a is equals to 9, and b is equals to what? B is equals to 2, right? So this is not scene, we add it to the scene set. Okay, just mark it as scene, right, like this. Actually, if it's on the screen, it's scene. Okay, fine. We do the add operation. Okay, so 5, 5, 4, 2, 4, 5, 3, 2, 3, 5, is that 2, 2, 2, 5, 1, 2, 1, 5, 0, 2, 0, 5, 9, 2, 9, 5, 8, 2, 8, query. Okay. 5, 7, 2, 7, 5, 6, to 6, and then we reach back here, 5, 5 to 5. Then we break, obviously. Oh, okay. Oh, that's not what I want. I want this instead. Then we do a rotation. Then we do a rotation. We do a for loop over B. For loop over B. I think there's some sort of like, okay, let's see. So n is equal to length of s, I think. And I think your loop should be n mod b. I think that's the number of loops. So if let's say it's 4, you rotate it just once. Yeah. If it's 2, you rotate it twice. So if it's 4 mod 2, you actually get 0. Oh, that's not good. Oh, maybe it's not mod, but divide. Yeah, so 4 divided by 3, you rotate it once. 4 divided by 2, you rotate it twice. 4 divided by 1, you actually rotate it, wait, 4 times, right? So just now from the example, when you rotate it twice like this, after one rotation you get this, and then another one rotation you just get one more like that. So that's why you only do a rotation once, right? But when b is equals to 2, you can rotate it once. Is this the upper bound? No, this means you rotate it twice. So 5, 5, you do this, you rotate, maybe, I'm not sure. This one, you actually want to rotate it 4 times. Okay, I guess we can try that. So for I in range of n divided by b, we actually need this outside. I guess we can put this as comments for now, for reference. So while s not in sync, we add this, we do the add operation. Afterwards, we want to do the rotate operation on s. Then if this is not in sync, we add it again, the add operation. Rotate, add operation. So because we're doing the add operation, the data structure would be more suitable. So we do this, q is equals to this. Then we will say timestir, I guess. Timestir is equals to dot join of q. So we say about timestir not in scene, we add timestir, we do the add operation on q. Then we rotate q and return bin of scene. Okay, now let's implement the let's move this out of the way. Yeah, maybe I don't need that, but I want to put the observations here at the top. So now we try to implement the add operation and the rotation operation, right? Or maybe I didn't explain this well enough, but for the queues in Python, it's actually a double-ended queue, so you can actually add to the end of the queue or the front of the queue in a pretty efficient manner. So in this case, because we want to simulate the rotation operation, that's what we want to do. I mean, that's a double-ended queue will allow us to do that efficiently. So we do the add operation on queue. So for I in range from 1 to the length of queue in a step of 2, we will say queue of I plus equals queue of I plus equals what? A. Okay, that's the add operation. For the rotation operation, rotates Q for I in range of B, Q dot top, Q dot append that. I'm not very confident. Oh, okay, what happened here? Oh, right, okay. Because that's an integer, and I also need to do the mod operation. So let's see. So timestir Q of I. That's a little bit of a pain. Actually, maybe it's not that bad. So we want to cast it into a bin first. Q of I plus A, but then the whole thing we want to mod it by 10, and then we want to pass this back to a string. Okay, that's not good, but let's take a look. That is interesting. We add timestir, we do the add operation on Q. Oh, we actually need to reassign it back like this, right? Let's see. Okay, this is a little bit better. 42. How many rotations have we done? Wait, is that it? This is correct. Okay. That is definitely not correct. Oh god. Let's see. N divided by B. Print two rotations, so 7, 4. Is it an implementation problem? Or is it like an algorithm problem? That's what I'm trying to figure it out. Or maybe we need to do this in like a smarter way. 1, 2. Let's see. What if this is 3? Or 4? Okay. Let's try this example. Oh, it's here. So we do 7, 4. We only do 2 rotations, right? 2 rotations. well, times 3 are not insane, so we'll try to modify this position, right? So 7, 9, 7, 4, 7, 9. Maybe I can print scene here. Seven, 4, 7, 9. Then we do a swap. So we go 9, 7. Wait, really? 7, 4, 7, 9. Let me see what's the state of Q. It's 4, 7. Oh, right, after we do the rotation. Okay, makes sense. So it's 4, 7. Try to minimize this. Ah, okay. So we add 4, 7. Then we have 4, 2. Actually, we can rotate it again. Maybe that's not like a fast brute force approach. Oh. So maybe it's an algorithm problem. Or maybe we need to do this better. How would we do that? Instead of brute force, we'll actually need to do something that is a little bit more optimal. A little bit more optimal. Sure, we have to get 24. Oh no. Uh, that is interesting. I feel like I'm getting closer a little bit, sort of, but the observation I'm making here is, at least for some random ass input, when B is even, fucking algorithm works. But um, when B is odd, I'm missing something. Right? See, the test cases are all passing when B is even. uh, is that really the case? This is 1, 3. Let's add 1, 7. Yes. Actually, I think 0 is a more interesting case. F9, sure, whatever. This is 4. Let's see if this passes. It doesn't, so that's not good. uh, okay. So I think we might actually need to change our room somewhat such that we can actually do this. And B is even can't actually change the even positions. That means in this case, you want to move the smallest even position to the front if you can, right? Then you just minimize what you can. When B is odd, because you can change the even positions in this case, what you want to do is, it's not that you can just change the even position characters. You can actually change all the indices. Is that true? Can change all the indices. Let's see, in this case, not this one. Maybe this one? Yeah. Oh, they result in the same answer. Oh, yeah, maybe. So let's see, this is 4. So the claim is that this results in the same answer. Is that it? Nope, they don't. They don't result in the same answer. Wait, they do. What the fuck? What the fuck? Am I cooking? Am I actually cooking? Wait, am I close? Shade. B is 4. When this is 2, it worked. uh, maybe it's not plus one thing. Interesting. Maybe that was just luck. But it doesn't change the fact that 2, how should I say it? Oh, wait a second. B is even. You can't change the even positions, but you can try every combination of the odd position changes. And when B is odd, it's not that you can change the even positions only, you can also change the odd positions, because that's what you can do already from the start. So it's kind of like saying, when B is odd, you can change every damn thing. When B is even, you can only change the odd position characters. I feel like range of B. I'm not sure. At least you got the even ones correct. Now that only the odd ones are wrong. I was just trying my luck there. Oh god damn it. Ah, fuck. I feel I'm so close. That's the fucking problem. Fuck. Okay, I'm thinking of like another approach, but basically we can try to group the even and the odd numbers together, right? So when we do the rotation operation, somehow just change out every point to that. I'm not entirely sure. But let's take this example, 5525. So 5, 5, 2, 5. This is 0, 1, 2, 3. Group all the even ones together and all the odd ones together. So I have 5, 0, 2, 0. 5, 1, 5, 3. Right? Thing is, can we? This is even. This is odd. So the claim is that if is B is odd, okay, if B is even, like 2, right? The best we can do, minimize this. Minimize this, doesn't really matter what A is. Yeah, it kind of matters. So A is equals to 9. We know that we can change this all the way to 0. All the way to 0. The even positions we can't actually touch. If it's even, we can actually change the even positions. But can we change their order? This is 2, by the way. Can we change their order? Can we always change their order? Five five 2 5 0 7. 5 5 2 5 0 7. 0 1 2 3 4 5. Let's test it out. B equals to 4. B equals to 2. B equals to 4. Right? That means for 2, we can move 0 7. Then it will be 5 5 2 5. We move 2 again. Right, but 2 5 is 0 7 5 5. We move 2 again, that'll be 5 5 2 5 and 0 7. Do we go back to the original? Yeah. How about this one? This one. Are there any states that we can't reach? If this was the case, right? All right, let's do that. Let's copy everything. So we move this 4 forwards. Right, 1 2 3 4. So that'll be 5 5 7, I think. What's the right rotation? Right rotations. Okay, let's do it one step at a time. Fuck. So this goes here. This goes here. Yep. Okay. 7 0 5 2. That's this one. Move this forward in. It's 2 5 5 5 7 0. That's this one. We move this forward in. Here is 0 7 5 2 5 5. That's this one, which is also the original string. So it does seem that, they are interchangeable. Is that the case for odd numbers as well? I think so. Yeah. Okay. Okay. That means there's only 2 answers. I mean, there's only one way to get. Yeah, you can always get the answer, right? Somehow. I mean, what I mean to say is the answer is the same when there's one answer when B is even, and there's another answer when B is odd. And the answer is always the same regardless of what B is, as long as B is even or B is odd, right? Okay. Oh shit, it's so hot. Yeah, I can't on the fan because it will affect the mic, but then it's too hot. Yeah. So how long is this video? I have no clue. Is that hour? Oh my god. Okay. what if B is odd? Let's remove this case. Fine, let's remove this case. So we do this, and do this. This is one. This is one. Oh shit. Okay. And for mine, 002502. It's a lot harder than I thought. Because no, that observation fails, right? I still think it's some greedy shit, man. It has to be. It has to be some greedy shit. Oh my god. Okay, let's see. Let's take a look at this one. 552507, right? 552507. B is equals to 1, and we're testing, and B is odd. We can actually change not just the odd positions, we can change all positions. Change any characters. And I should change the position characters. Okay. Because we can change any position that we want. Wait, that's not true anymore, right? You see? Yeah, maybe it's not true. At least for this case, this is true. What's the 9? So we can actually get this down to 0. So it's 5, 0, 2, 0, 0, offset by 2. Then we move it by 1, maybe 2, 5, 0, 2, 5, 0, 2, 0, 0. Try to minimize this. So maybe 2, 4, 0, 1, 0, 0, 2, 3, 0, wait, 2, 4, 0, 1, 0. This is 9. Let's do 3, 0, 0, 0, 8. Then we can do a rotation until we get 0, 0, 0. Okay. 8 to 3, I think. Yeah, okay. So let's modify the base equals to 3. Base equals to 3. Base equals to 3. Okay, we will try to minimize this first. Yeah. Then we do a rotation of 3. So we 5, 0, 2. Then you put the 2 here, and 0 and 0. Apparently that's the best that we can do. Oh, okay. Okay. We say, hey, can we do any better than this? Well, in this case, we actually can't. 0, 9, right? A is 9. A is 9. But this is already the best. There's no, yeah, okay. doesn't change the fact that we can only do one rotation, and then we can check all the answers, right? Three. And divided by plus 1. I want to see the state of Q. Get this, then you go back. A. Oh, okay. You want to take the min of all of what you have. Yeah, you want to take the min of. Oh, you want to take the min right now. Your current set of really. Current set. Yeah, we just say best, I guess. Best is equals to 9 times 9 times 10. Is it n? Yeah. Min of c. This is best. Print q times 2 join q. So you want to update q, right? Q is equals to min min of c. So what do we have in C? C will be a string, a string. So min of C will be a list, and we need to wrap it into a queue. Oh my god. The queue, and then we do the rotation. Min of best. I don't know. Yes. Holy fuck. Okay, what the fuck is wrong here? Just need one more rotation. N is 6. Plus 3. That's so sus. That is so sus. Now you would think plus 1 is good enough, but it's not. And I'm not even sure or confident that this is correct. Okay, but I could give it a try. Wrong answer, obviously. Let's see. Rotation is 3, so if B is odd, you can actually change any characters. Take the even one out. Let's try this. Print Q. This is the best of the one rotation. That's the claim. That is the claim. That's true. So it's not rotated yet. No, I need to see what is the one here, right? Minimize this. That's a 7. Oh, this was 0. This would be 8. 1, 2, 3, 4, 5, 6, 7, 5. 6. 6 plus 6 plus 7. 1, 2, 3, 4, 5, 6, 7, 3. This is 1. 4, 0, 9, 5, 7, 3, 5, 1. Then we do the rotation for 3. So that'll be 1. Okay, we do the rotation here. What would that be? That'll be 1 here, 5 here, 1, 5, 3. Yep. Oh, gee, I should do this. Then we minimize this. And the answer here is 030. Wait, how the hell they get this one? Okay, how would I do it by hand? I kind of would have done the same thing. So you minimize this. Then you rotate it. Oh, never mind. I think I'm off my depth. Let's see how to solve this problem. It's a good attempt. Topics, depth for search, breadth for search. Interesting. Enumeration. What the hell is this? Okay, let's give it a quick read. Note that when S is even and B is even, and regardless of how many rotations, we can only apply the operation to the odd elements of S. That's actually the observations that we have made, right? So when S is even, where S is always even. When B is even, okay, only, yeah, B is odd, both the odd and even number positions, and each potentially a different number of times. Okay, seems to be some sort, okay. You can see that a number of cumulative are independent of each other. The number of operations does not affect whether when positions are accumulated. Hmm. Hmm. Okay. Well, it's a valid attempt. I probably have to reread the editorial. Um, yeah, when I have time or whatever. Well, okay, it's cool. It's cool. Anyway, thanks for watching, guys. This was the problem of the day. Didn't really manage to solve it. Maybe I'll revisit this sometime in the future. Thanks for watching and happy grinding.